Hi students, and welcome back to chapter 7 and 8. When we left off, we were talking about the different types of bonds. So we have already discussed that there are two types of chemical bonds, ionic and covalent. And when we have a covalent bond, it can be either unevenly shared in a polar bond or evenly shared in a nonpolar bond. And then of course, nonpolar bonds have the intermolecular force of van der Waals when they create a dipole moment. And polar covalent bonds can either interact in a dipole-dipole or in even a stronger hydrogen bond where we still get these kind of partial positives and partial negatives attracting each other. The next type of bond that we're going to talk about is the other option, when we don't have just a sharing of valence electrons, but instead when we have the complete transfer of valence electrons resulting in the formation of a cation, which remember is positive because cats have pos, and an anion, which is negative. And what happens next for those ions is that they start to form something called an ionic bond. Most of Earth's rocks and minerals are made up of ionic bonds. These are very commonly naturally occurring items. This is when we've seen an atom that gains or loses an electron to form either a positive cation. So remember, cations have lost electrons because electrons are negative. So if you lose negative, you become positive. So cations are positive, and then we have our anions, which are negative. They have gained electrons, and those cations and anions then interact together, and the positives attract the negatives. Remember, opposite charges attract, like charges repel each other. The positive and negative attract each other in such a way that the positives equal the negatives. So if we have something like Na and Cl, there's one sodium and one chlorine, so the positives, the Na plus, equals out a single negative of Cl minus, and that makes a total neutral NaCl. So this is one example of an ionic bond. So once again, for an ionic bond, we get this complete transfer of an electron. So in this case, sodium has one valence electron, and it doesn't want to have one. Remember, it wants 8. So it's going to give this one electron over to chlorine. Chlorine then gains that electron, giving chlorine a total of 8 valence electrons. Remember, chlorine is a halogen, so it typically begins with 7. It gains an electron, so we form Cl minus. Meanwhile, sodium lost an electron, so it's Na plus. And now, this is the ionic bond part, the negative of chlorine attracts the positive of sodium, and so we end up with this repeating Cl minus Na plus, Cl minus Na plus, and all together that compound becomes neutral. This, by the way, just in case you don't remember, is table salt. So when you go to the salt shaker and you take salt out of the salt shaker, you are taking out a crystal of these repeating sodium, Na pluses, and Cl minuses. So we call that most reduced version of the compound, the single formula. We call that the formula unit. So this right here, NaCl, is a formula unit, okay? That is how we represent a formula of sodium chloride. But this whole thing that's shown here is considered its crystalline lattice. So the formula units kind of are like a single Lego, and then we add those Legos on top of each other until we make this big ionic compound. So ionic compounds can be much larger than individual molecules. They are made of repeating formula units, and those formula units are put together in such a way that the positives equal the negative. So this is showing you a picture of the crystal lattice. And so the crystal lattice is this kind of big structure that is created from those individual formula units stacking on top of each other. So guys, crystalline lattice and formula unit are two vocab terms that have to do with ionic compounds. They're from chapter 7. And always on the test, People miss these two vocab terms because there's not enough exciting stuff going on right now, and so they don't really pay attention to the difference between a formula unit and a crystal lattice, and then they miss that problem. Please don't do that. So if we look at this example of rutile here, so this is rutile, the actual crystal, and then this is a model of it. The formula unit is the single red with the single gray piece. The crystalline lattice is this whole structure that we're seeing here. So a crystalline lattice is a compound made from all of the repeating formula units of an ionic compound. Okay, so now we just want to compare characteristics of molecular and ionic compounds. So we have been talking about molecular compounds earlier in the chapter. Molecular compounds are two non-metals. So something like compounds like FCl, HF4, and HNO are all non-metals. If you don't already have something like this written down in your notes, please make sure you do it right now. HCl, HF4, HNO3, those are non-metals bonded together. They are molecular compounds. They are covalently held together. So these molecular compounds have low melting and boiling points, and they tend to be gases at room temperature because the intermolecular forces that are between them aren't necessarily strong enough to hold them together as solids. On the other hand, ionic compounds, like the ones we were just talking about, ionic compounds combine a metal and a non-metal. Again, if you don't have this written down somewhere, you should do it now. Ionic compounds are between a metal and a non-metal. They're things like NaCl, MgCl2, and LiS, and we call those ionic bonds. And so ionic compounds have high melting and boiling points because of the formula unit crystal lattice situation, where each of the formula units are kind of bonded to the next formula unit as well, which holds them together even stronger than any of the intermolecular forces that we see in covalent molecules. When ionic bonds become molten, or when they get dissolved in water, they're good electrical conductors because the cations and the anions allow for electricity to kind of move its way or snake its way through the liquid. And we say that ionic compounds are hard but brittle. Hard but brittle is like glass. Okay, glass is a good example of hard but brittle. It would hurt to get hit with a pane of glass, but as it hurt to get hit with it, you would also probably shatter the glass. And so they are hard, that hurts, but they're brittle, that breaks. Okay, so ionic compounds are considered hard but brittle. And this is a really important thing to consider down here. It says that in chemistry, ionic bonds are considered stronger than molecular bonds. That's because there's this kind of overall strength to them. But ionic bonds are so strong only when they're dry, meaning there's no liquid around, there's no water. As soon as an ionic bond gets in water, it dissolves and it breaks apart, right? They get dissolved in water, they become good electrical conductors, and they exist as ions. So in biology, when I'm teaching biology, I say that covalent bonds are the strongest, but when I'm teaching chemistry, I say that ionic bonds are the strongest. That's because chemistry is primarily existing in a dry environment, and chemistry goes far beyond the reaches of just Earth, right? Or just humans, or just life. Chemistry goes all the way to the outside of the universe. So in biology, when we're only concerned with human structures or living structures, those structures are made of water, and so the ionic bonds are all dissolved already. We'll talk about that a little bit in class, but it's an important thing to know as a person studying science, as a scientist. So in our big picture, we have talked about two types of chemical bonds. We just recently talked about ionic bonds, which involve the complete transfer of an electron from the cation to the anion. And then those cations and anions stick together in formula units and stack up to form a crystalline lattice. We've also talked about covalent bonds, which can evenly share bonds in a non-polar covalent bond, or they can have an uneven share in a polar covalent bond. Polar covalent bonds then go on to have dipole-dipole and hydrogen bonding as their intermolecular forces, where nonpolar bonds go on to have van der Waals or London dispersion interactions. Before you get to the test, you should be able to look at this diagram and talk through it much in the same way that I just did. It would be a great idea to listen to that part again, to practice saying it, to make sure you can get all of your correct vocab terms, because remember, guys, that the 7 and 8 test is your final and is counting as a big chunk of your overall chemistry grade.